Okay, so for the next one, we are to place the following transfer function into standard form and generate Bode magnitude and phase plots, and also what is the damping factor of the quadratic term. So to get it into standard form, we need to get all of our factors to be 1 plus something or 1 minus something. So in the numerator, I need to factor out this. That says times 10 to the negative 2. You can't see it. I will factor out a 10, and I'm left with 1 plus j omega. And in the denominator, I have j omega, and I'll factor out a 16, and I'm left with 1 minus omega squared over 16 plus j omega over 4. And now I need to get all of this into standard form. So 8 times 10 to the negative 2 times 10 over 16j. That is our constant term, which I'll get to that in a second, what that is. And then 1 plus j omega, that's a simple 0. And then I have omega, and that is a pole through the origin. And then this quadratic term, I need to have it in the form of 1 plus, so I'm going to write the form and then we'll fill in the blanks. So 1 plus 2, and I think your book uses the Greek letter xi. It's usually the Greek letter zeta, so I don't know why it uses xi, but 2 xi omega over omega c plus j omega over omega c squared. That is the standard form. So now we have to figure out, well, then if that's the case, what is omega c and what is xi? So it's easy to see that if j over omega c squared has to equal negative 1 over 16, then omega c has to be 4. So we've got that. And then that means that, so that's using this term, and then 2 xi omega over omega c equals, that's this term right here, or I guess there's a j in there, there's a j, equals j omega over 4. So this tells us that so omega c, we just found out that was 4. So 2 j omega times c over 4 equals j omega over 4. So 2 xi has to equal 1, or xi has to equal 0.5. So that's our damping factor. And omega c is 4 for the quadratic term. So now let's figure out our constant. So our constant is, if we do 8 times 10 to the negative 2 times 10 over 16j, you get minus, shouldn't the j stay down? I brought it to the top.
Isn't j omega like the denominators?
So the pole for the origin is just the omega. Yeah, so the pole for the origin is just the omega, not the j. The j, it goes with the top. So I would get minus j 5 times 10 to the negative 2. And what this tells me, and it's, okay, this was a problem from the book, but I didn't see that it told you this in the book. So our constant term is really 5 times 10 to the negative 2. What the minus j does is it's for the phase. So if you recall, for the phase, if the constant is greater than 0, then your phase for that part is 0. If your constant is less than 0, then your phase is plus or minus 180. But if you have, if it's imaginary, if it's purely imaginary, if you have plus j, then your phase is 90 degrees, and if you have minus j, your phase is negative 90 degrees. So this gives us a phase of negative 90 degrees. Or did they have that built into the pole?
That's what I was thinking.
Okay, so it's might be a different way of doing it. So I might be doing it a different way. So if you had it,
I feel like the examples he's done, he's read to me.
If I recall from Friday, did we say we didn't have to grab the phase?
Oh yeah, I would
oh, you don't have to grab a phase plot?
I'm not sure.
He said we only have to do magnitude.
Do you lie about that though?
I hope not.
No, I don't think so.
No, he wouldn't. He would not. He would not. He would not say that and then give you one. Or if he says that and gives you one by accident, don't spend a lot of time on it because he will make it good. You know, he will.
He spent like 20 minutes reviewing it, and then he said, "Jokes on y'all, y'all don't even know that the test." So.
Okay. Yeah. So I would not.
What's that variable that you? I can't.
Oh, the Greek letter xi. He might. So I call it xi because I also study ancient Greek, and so I use classical pronunciations. I say phi and xi and ki and not phi, xi and chi. So it's
Looks like chicken scratch.
it does. It's officially.
I'm really trying to get into it.
So this is from many years of actually writing Greek. It's yeah. That's the letter.
That looks like an inductive.
Okay, so and I write it like I put a little curly and then a that. That's but then I do it, but it looks a lot like a zeta, which is like that, which is what most books use for this. And so I don't know which one he has been using in class.
How are you able to say that first line? J2 damping factor. Yeah, that one.
How am I able to say it?
Yeah. Why? Why is that equal to each other?
Oh, okay, because this is the form of the quadratic pole. That just is. That has nothing to do with our problem. And then our problem had 1, if I put it in order, 1 plus j omega over 4 minus omega squared over 16. So minus omega squared over 16 had to equal j omega over omega c squared. And from that, I got that omega c equaled negative 4.
Oh, I got it.
And now you see where I got it from.
Yeah.
So then I just took this and set it equal to that, and that's where I got it from. Did you find it?
Yeah. It's just.
But this is definitely
Something like this. Yeah.
something like project.
Okay, so he does put the J down there. Okay, so there's a different way of, different ways of doing things. So if we keep the J down here rather than up here, then we say that this is the pole through the origin, and that's what gives us the minus 90 degrees. Although was it? Yes,
And that
yes,
would just
that's
be a
right.
Constant on top.
And it would just be a constant on top. Yep, yep. Okay, but if we don't have to do the phase plot, then I am not going to do the phase plot unless y'all have, I'll do it later. I'll post it later because you might have to do it on the exam, but I'm not going to do it right now.
I trust his most of his
You trust what?
I trust most of them, like so.
Oh, no, but I mean for the final exam.
Oh.
Yeah. Okay, so we have the constant is 5 times 10 to the negative 2. So we need to take 20 log of that. 5 times 10 to the negative 2. And I believe that gives us minus 26 decibels. And then we have a zero factor with omega c equal to 1 radian per second, and that's from 1 plus j omega. And we have a quadratic pole with omega c equals to 4 radians per second, and that's this pole right here. And we had the j omega in the denominator, and that gave us the pole at the origin. And so we know that what we're going to do in a minute, well, let me just go ahead and grab the graph. How did you get the damping factor in your transfer function? I see your math, but I don't know how you get it from the transfer function. Okay. How did I do it? Okay. I did just explain that. If you didn't catch it, I'm happy to explain it again, but just in case the question came from before I explained it. Oh, really? Time is... Okay. Do y'all still need that? I'm happy to do it again if y'all still need it. Yes. Okay, I will keep an eye on this. So what if y'all still need the damping factor, I will come back and do it. So just but just let me know. He wouldn't. Well, he wouldn't do it on purpose. Okay, so I will start with my negative 26, which was from my constant term. Okay, then from my simple zero, which was 1 plus j omega to the first power, that's going to give me a slope at 20, starting at the corner frequency. So it goes 0 until I get to 1, that's the corner frequency, and then it is 20 decibels per decade, so that goes to 1 to 11 would be the slope there. And this one is from 1 plus j omega. Okay, then I have my pole through the origin, and a pole through the origin goes through 1 and has a slope of negative 20. So it goes through 1, has a slope of negative 20. So that would be, wait, did I make this go? I did, I went too far, hold on. It's not a good slope. 20. And then this one will have negative 20. And so this one is the pole, j omega. This one is the simple 0. And then I have my quadratic pole, and my quadratic pole, I take my corner frequency, which is 4, and let me make sure I get this right. It's the slope, because it's a pole, it's negative, and it'll be negative 40 because it's quadratic. And yeah. Okay, so it goes from, from 0 to 0.4, it'll be at 0, and then from 0.4 to 40, we'll have a slope of negative 40 decibels per decade. And then once we get to 40, it's going to go back to 0. So it will look like,
Is that when he says go up a decade and go down a decade and continue the slope? Similarly, this uses the corner frequency, and then he says go up a decade and then go down a decade.
he just uses the corner frequency and says go up and down. Oh, that makes sense.
Yeah.
Yeah. Starting where?
I guess from the center.
Starting from at 4?
Yeah.
Yeah, I think we need to go. So this is actually true for the phase. So I was getting the phase confused. So no, we just want to go to the corner frequency and have a slope of negative 40. Yep. So we'll go to the corner frequency, and we have a slope of negative 40. So we'll go down 2. So to the corner frequency, which is 4. 1, 2, 3, 4. And then I'll go down a decade, so I'll go down 40. And so it'll look like that. Yep. There's also a chat. I'm just having trouble understanding where he comes from. Okay, yeah, so I will come back to that. After I finish the graph, I'll come back to that.
You have the constant as 5 times 10 to the minus 2, right?
Yes?
I'm getting minus 3.
Did you forget the 10 that you factored out of the 1 plus j omega?
Right, yeah, that's true.
Yep. Okay. So now, to put these all together, I have I'm going to start at 0.1 rather than over here at 0.01. So at 0.1, my pole was at 20, and my constant was at negative 26. So that would put me at -6. So I just add those together, add those numbers together. And then the only slope that I've got until I get to 1 is this slope of minus 20 decibels per decade. So I can go over 1 decade and down 20, so I'll end up here. And then when I get to 1, I can see that what I added was a slope of plus 20 decibels per decade. So now I have a slope of minus 20 decibels per decade and plus 20 decibels per decade. So those two will cancel each other out and make a 0 slope until I get to where my next piece starts, which is at 4. And then at 4, I am adding on a negative 40 decibels per decade. So that's what's changing here. And so that's going to make another slope of negative 40. So from here over to the next decade, I'll go down 40. So that's at minus 26, so minus 66.
Just follow the same slope.
It does. It has the same slope. The same as the red slope.
Yeah. How did you do the first portion of
I started at 0.1. Yeah, I didn't do anything before 0.1. But I mean, I could, and it would just be,
go the same.
yeah, yeah. Okay, so let me go back to answer the question about the damping factor. And so we had the quadratic term of 1 minus, let's see, 1 plus j omega over 4 minus omega squared over 16. So that was our quadratic term. And the form for the quadratic term is 1 plus 2c j omega over omega c plus omega over omega c j omega over omega c squared. And so if I can find out what c is, that is my damping factor. And so I start by finding my corner frequency. I start by saying j omega over omega c squared equals minus omega squared over 16. So I go to my omega squared term. J squared is minus 1, so that's minus omega squared over omega c squared equals minus omega squared over 16, which tells me omega c has to equal 4. So now I go back and I plug omega c into this, and I get 2cj omega over 4, because I just found that, and that has to equal this term. It has to equal j omega over 4. So now I'm just solving this equation for c. So if I divide both sides by j omega, multiply both sides by 4, I get that 2c equals 1, or c equals 1/2, c equals 0.5. And that's how I got my damping factor. So, other questions?